You know that sound, that really distinct change in pitch, like an ambulance siren or maybe a train whistle when it's coming towards you, passes and then goes off into the distance.
Oh, yeah, absolutely. It goes from that high-pitched no yow down to low, WW woo.
Exactly. That shift, higher as it approaches, lower as it moves away. Well, almost everyone's heard that. And it turns out it's not just some random thing. It's actually a perfect everyday example of some really fundamental physics, a principle that applies to all sorts of waves.
That's right. And that phenomenon is what we're going to dig into today. It's called the Doppler effect. It's a really core concept when you study waves, and it shows how our perception of things like sound or even light gets influenced just by motion.
Specifically the relative motion, right?
Yeah.
Between whatever's making the wave and whoever's, well, observing it.
Precisely. And, for anyone really looking to get a solid grip on physics, especially, say, for something like the GCE A physics syllabus, understanding the Doppler effect inside and out is, well, it's pretty crucial.
Absolutely. And we've got some great material here that really lays it all out, the basic idea, why it happens, and maybe surprisingly, where else it shows up. We're talking speed guns, distant galaxies. It's got quite a reach.
So that's kind of our mission for this deep dive, wouldn't you say? We'll unpack this effect using this material, figure out not just that the pitch changes, but the physics of why, and then explore some of those maybe unexpected applications.
Yeah, let's do it. By the end, you should have a really clear picture of how this relative motion thing shapes how we perceive waves all around us. Okay, so let's start at the beginning. Fundamentally, what is the Doppler effect? What are we actually talking about here?
Okay. At its core, the Doppler effect is the apparent change.
Yeah.
And apparent is the key word here. The apparent change in the frequency, and because frequency and wavelength are linked, also the wavelength of a wave.
Apparent, meaning it just seems to change to the observer.
Exactly. It happens purely because there's relative motion. Either the source of the wave is moving relative to the observer, or the observer is moving relative to the source, or maybe both are moving.
Right, so it's not like the source itself, say the train whistle, is actually changing its tune. Its vibration frequency is constant.
Precisely. The whistle is putting out sound waves at a steady frequency from its own perspective. We often call this the source frequency, or $40. It's what you'd measure if you were riding on the train right next to the whistle.
But if I'm standing still and the train's moving relative to me,
then the frequency you perceive, let's call it $5, can be different from $5, and that difference is the Doppler effect.
okay, and the classic example, the one in the material too, is that train horn or maybe a siren. As it comes towards you, the pitch sounds higher, higher perceived frequency. Then as it passes and moves away, the pitch drops noticeably, lower perceived frequency. That clear shift from high to low, is the Doppler effect for sound. The source frequency, $30, stayed the same, but the perceived dollars changed.
That's the perfect illustration. And, just for a little historical context, it was an Austrian physicist, Johann Doppler, who first described this back in 1845. He initially focused on sound, explaining that pitch shift.
But it applies more broadly.
Oh, yeah. The principle works for any kind of wave, as we'll see, light included.
All right, so we get that the frequency appears to change due to relative motion. But the really interesting bit, especially if you're digging into the physics, is why. What's actually happening with the waves?
It really boils down to how that motion affects the spacing of the wavefronts when they reach you, the observer. Let's think about sound waves in air. Picture them like expanding bubbles or crests moving out from the source.
Okay, like ripples, but in 3D.
Exactly. Now imagine the source is just sitting still, maybe emitting one wave crest every second, and you're standing still too. How often do the crests arrive at your ear?
Well, if it emits 1 per second, and I'm not moving, I should receive 1 per second. The frequency I hear matches the source frequency.
Perfect. Now, let's get things moving. Say the source starts moving towards you, but it's still pumping out those crests at the same rate 1 per second.
Okay.
It emits the first crest, then 1 second later, it emits the second crest. But in that 1 second, the source itself has moved closer to you.
Ah, I see. So the second crest starts its journey from a point that's closer to me than where the first crest started.
Precisely. And the third crest starts from even closer, and so on. In the direction the source is moving, each wave crest it sends out has a slightly shorter distance to travel to reach you compared to the one before it.
So the waves are getting bunched up,
Yeah.
compressed in the forward direction.
That's a great way to put it. The motion of the source effectively bunches up the wave fronts in front of it. Think of it like cars on a highway getting closer together when they approach a slow-moving truck.
Okay, so the physical distance between those wave crests, that's the wavelength, right?
Right.
Lambda. That distance gets shorter in front of the moving source.
Correct. The wavelength, perceived by the stationary observer in front, becomes shorter than the original wavelength emitted by the source.
And how does that affect the frequency I hear?
Well, remember the basic wave equation. Wave speed equals frequency times wavelength, so phi aculus joules lambda. Now, the speed of sound in the air is pretty much constant, assuming the air itself isn't moving like crazy.
Right.
So if the speed L is a constant and the wavelength lambda gets shorter due to the source's motion towards you, what must happen to the frequency dollars for the equation for any lambda to still hold true?
If lambda goes down and the V is constant, F must go up, higher frequency.
Exactly. Shorter wavelength means you encounter the wave crests more frequently. That's why you hear a higher pitch when the source is approaching you.
Okay, that makes sense. And I assume the opposite happens when it moves away.
You got it. If the source is moving away from you, each crest it emits starts from a point further away than the last one.
So now the waves are getting stretched out behind it.
Perfectly described. The distance between successive crests reaching you increases. The perceived wavelength gets longer.
So lambda increases. And since 4 exhaust, lambda goes up, F must go down.
Yeah.
Lower frequency, lower pitch.
Precisely. The crests arrive less frequently at your ear. The diagrams in the material, I think they're labeled figures 6.2 and 6.3, they show this really well, the bunching up in front and the stretching out behind a moving source. It's all about how that motion changes the spacing of the waves in the medium.
Okay, that conceptual picture of wavefronts bunching or stretching is really helpful. Now, the material also gives us the actual formulas to calculate these frequency shifts in different situations. These are pretty important for, actually solving problems.
Absolutely. Nailing down the formulas is key. The material breaks it down into the main scenarios, depending on whether the source or the observer is moving. Let's take them one by one.
Sounds good. First up, source moving, observer stationary.
Right. Scenario 1. Source moving towards a stationary observer. That's figure 6.2. The source, let's call it S, moves with velocity O towards observer O, who's just standing there. The source emits waves at its natural frequency, $2.
And we said the waves get bunched up. How does the formula capture that?
Okay, let's think about one cycle. The time for one cycle is the period, $t, which is just $100. In that time, $t, the source moves forward a distance to times $t. A wave crest emitted at the start travels a distance 5 times $t, but the next crest is emitted from a point that's $4 closer.
So the distance between those crests, the wavelength the observer sees, is the distance the wave traveled minus the distance the source traveled in that time.
Exactly. The effective wavelength lambda in front is lambda VT0 UST dollars. We can factor out $t, so lambda VUST.
And since $t, that means lambda frac VUST, and that's the shortened wavelength.
Correct. Now, the frequency the observer perceives, sum for dollars, is the wave speed dollars divided by this new shorter wavelength lambda. So $4 for FVUST.
And if you rearrange that, you get 5 SVUS. That's the formula given.
Precisely. Now let's look at that formula. 5 FVUS. Since the source is moving towards the observer, nu c is a positive speed. The denominator is 5 minus something positive, so VUSC is smaller than 5.
Right, which means the fraction frac is greater than 1.
Exactly. So 5s is greater than 1 times SO1. The perceived frequency for S is higher than the original sever. It matches our intuition. Source moving towards means higher frequency.
Okay, makes sense. Now, scenario 2. Source moving away from the stationary observer. Figure 6.3.
Same setup, but now source S is moving away from O with speed 99. The waves behind it get stretched out.
So, following the same logic, in one period $t-ness, the source moves UST further away, the wave travels VT dollars, so the distance between crests behind it is the sum now.
You got it. The effective wavelength lambda behind the source is lambda VT0 plus UST0 plus UST dollars V plus US.
Which is lambda frac plus USUV, a longer wavelength.
Correct. And the perceived frequency, $5, is again for lambda, so 5 OVV plus US lore.
Which simplifies to 5 EV plus USOV, the second formula.
Yes. And let's check this one too. Source moving away, USCD is positive. The denominator is Raller plus USL, which is larger than 5 O's.
So the fraction for V plus USD is less than 1.
Meaning 5 equals less than 1, text something less than 1 times SS. The perceived frequency valor is lower than the original of it. Again, it confirms what we expect. The source moving away means lower frequency, lower pitch. Here's where it gets really interesting, seeing how the math just falls out from the physical picture.
Okay, that covers the source moving. What if the source is stationary, but I'm the one moving? Observer moving, source stationary.
Good question. Scenario 3. Observer moving towards a stationary source. This is figure 6.4. Source S is still emitting waves at a few dollars, which have a wavelength lambda equals VSDO in the medium. Observer O moves towards S with speed U dollars.
Okay, so now I'm moving into the waves. Like walking into the rain makes you get wetter faster. I should encounter the wave crests more often.
Exactly the right analogy. The waves are coming at you with speed of valor dollars relative to the air, but you're also moving towards them with speed she brings. So the speed at which you and the waves are closing in on each other is valor plus U dollar.
That's the relative speed of encounter.
Right. The frequency you perceive is how many crests you encounter per second. That's going to be this relative speed of encounter divided by the distance between the crests, which is the original wavelength lam dollars. So 5 actx relative speed.
Lambda, so if we substitute that, 5 actx plus UO.
Which rearranges to 5 actx plus UO. That's the third formula.
Let's check the logic. Observer moving towards UL is positive. The numerator, valor plus UA, is bigger than valor. So the fraction frac S plus UA sound is greater than 1.
Meaning 5 hours, higher perceived frequency. Again, matches our intuition. Moving towards the source means you hear a higher pitch.
Makes sense. Final simple case. Scenario 4. Observer moving away from a stationary source. Figure 6.5.
Right. Observer O moves away from stationary source S with speed. The waves are still traveling at speed nullars towards where the observer was.
But I'm moving away from them now, so I'm kind of running away from the crests as they try to catch me. I should encounter them less often.
Exactly. You're moving in the same direction as the waves are propagating. The relative speed at which the crests catch up to you is now VUO barler, assuming you're moving slower than the waves, VUO bar.
Okay, so the perceived frequency is, again, this relative speed divided by the wavelength lam dollar store.
Yep. And substituting lambda bound viral gives 5 VOVOVO.
Which is 5. Fra VUOV is 5, the fourth formula.
And let's check. Observer moving away, Shiro is positive. Numerator VUO is smaller than VUO. The fraction fra VUO is less than 1.
So $5, lower perceived frequency, matches perfectly. Moving away from the source means lower pitch.
Okay, so those are the 4 basic building blocks. Source moving towards away, observer moving towards away.
But what if, say, both the train and I are moving? How do we handle that? That seems like the most general situation.
It is, and there's a combined formula for that, which the material gives in section 5. It basically puts together the effects we just looked at. The general formula looks like this. 5 time is left, SUE, MPUS.
Whoa, okay. Plus minus on top, minus plus on the bottom. That looks potentially confusing. How do you know which signs to use?
Yeah, it takes a second to parse, but there's a clear logic. You choose the signs based on whether the specific motion of the observer or the source would tend to increase or decrease the perceived frequency compared to if they were stationary.
Okay, let's unpack this. Let's start with the observer speed, $2 in the numerator.
Right. Think about the observer's motion. If the observer moves towards the source, does that increase or decrease the frequency they perceive?
Moving towards. They encounter waves faster, so higher frequency.
Correct. To make the overall fraction larger for higher frequency, we need the numerator to be larger. So we use the plus sign. Vi plus UOA.
Okay. And if the observer moves away from the source?
They encounter waves less often, lower frequency. To make the fraction smaller, we need the numerator to be smaller, so we use the minus sign.
Got it. So for the observer in the numerator, plus is moving towards source, minus is moving away. That matches our earlier formulas.
Exactly. Now for the source speed, USLers in the denominator. Think about the source's motion. If the source moves towards the observer, does that increase or decrease the perceived frequency?
Source moving towards, bunches waves up, shorter wavelength, higher frequency.
Right, higher frequency. Now, how do we make the overall fraction left larger using the denominator? We need to make the denominator smaller.
So we need to subtract USLer. We use the minus sign. USLer.
Precisely. Source moving towards the observer means we use USLers in the denominator.
Okay. And if the source moves away from the observer?
Source moving away, stretches waves out, longer wavelength, lower frequency.
Lower frequency. To make the overall fraction smaller, we need the denominator to be larger.
So we need to add US plus, we use the plus sign, volars plus USC.
Okay, let me try and summarize the sign convention for the general formula forego, US 11O US right. Numerator. Use plus letter if observer moves towards source. Use US if observer moves away from source. Denominator, use US letter if observer moves towards observer. Use plus zeros if source moves away from observer.
That's it, exactly. You look at each motion independently, observer relative to medium, source relative to medium, decide if that specific motion would raise or lower the frequency, and pick the sign in the numerator or denominator accordingly to achieve that effect.
It seems a bit fiddly, but the logic holds. You just have to apply it carefully for each case.
Now, we've been talking mostly about sound waves because that's where we hear the effect most obviously with pitch changes. But it's really important to remember this isn't just about sound.
Right, you mentioned it applies to all waves, so light waves too.
Absolutely. The Doppler effect works for electromagnetic waves like light as well. The core principle is the same. Relative motion between the light source and the observer causes an apparent shift in frequency and wavelength.
Is it exactly the same, though? Because light is weird, right? Doesn't need a medium. Speed is constant.
That's the crucial difference. Light travels in a vacuum. Its speed, $6 is constant for everyone, no matter how they're moving. That brings in Einstein's relativity for a fully correct description, especially at very high speeds. However, for speeds much less than light speed, the classical ideas we've discussed give a very good approximation, and that's what the material focuses on.
Okay, so how does this shift show up with light? We don't hear colors change pitch.
No. With light, the change is in the perceived color. Remember, the color of light depends on its wavelength or frequency. Higher frequency light is bluer, lower frequency light is redder.
So if a light source, like a star, is moving away from us,
then the light waves reaching us are effectively stretched out, just like the sound waves from a receding siren. The perceived wavelength gets longer than the wavelength lambda dollar that was actually emitted.
Longer wavelength light is redder. So the light shifts towards the red end of the spectrum.
Exactly. And that phenomenon has a famous name, redshift.
Redshift. Got it. So seeing redshift tells us something is moving away.
Precisely. And conversely, if a light source is moving towards us,
the waves will be compressed. Shorter wavelength, which is towards the blue end of the spectrum.
You got it. That's called blue shift.
Red shift for moving away, blue shift for moving towards.
That's the key. And what's fascinating here is this isn't just theoretical. Astronomers use this constantly. Stars and galaxies contain elements that emit or absorb light at very specific known wavelengths, like fingerprints in the light spectrum, spectral lines. Exactly. If the star or galaxy is moving relative to us, those fingerprint lines won't be exactly where we expect them in the spectrum. They'll be shifted slightly towards the red if the object is receding, towards the blue if it's approaching.
Wow. So by measuring how much those lines are shifted?
Astronomers can calculate the object's speed towards or away from us, its radial velocity. It's an incredibly powerful tool. In fact, the observation that light from almost all distant galaxies is redshifted was the crucial evidence that led scientists to conclude the universe itself is expanding.
That's amazing. The same basic physics explains a passing train whistle and the expansion of the entire universe.
It really is quite profound when you think about it.
Okay, so astronomy is a huge application. What else? The material mentions some more down-to-earth uses too.
Oh, definitely. The Doppler effect is built into a lot of technology we use every day. Think about police radar guns for measuring vehicle speed.
How do they work? Is it like the light shift?
Similar principle, but using radar waves, which are a type of electromagnetic wave like microwaves. The gun sends out radar waves of a known frequency. These waves hit a moving car and bounce back.
And because the car is moving, the frequency of the reflected waves is shifted.
Exactly. If the car is coming towards the gun, the reflected waves come back at a slightly higher frequency, a blue shift, essentially. If the car is moving away, they come back at a lower frequency, a red shift.
And the gun measures that frequency difference.
Precisely. It compares the frequency it sent out with the frequency it gets back. That difference, the Doppler shift, is directly related to the car's speed along the direction the radar is pointing. The gun does the calculation and boom, it displays your speed.
Clever. So that's how they catch speeders.
Yep. And another really important area is medicine, using ultrasound. The material specifically mentions this, I think on page 61. Ultrasound uses high-frequency sound waves way above what we can hear.
Or like for pregnancy scans.
That's one use, but Doppler ultrasound is specifically used to look at motion inside the body. Think about blood flowing through your arteries and veins.
Blood cells are moving.
Exactly. So if you send ultrasound waves into a blood vessel, they'll reflect off the moving blood cells. And just like the radar waves bouncing off a car, the frequency of the reflected ultrasound waves will be Doppler shifted.
So if the blood is flowing towards the ultrasound probe, the frequency comes back higher.
Yeah.
And lower if it's flowing away.
You've got it. The machine measures this frequency shift, and from that, it can calculate the speed and direction of the blood flow. Doctors use this all the time to check for things like blocked arteries, problems with heart valves, evaluating circulation. It's a non-invasive way to see how things are moving inside you.
That's incredible. So the same physics, a train whistle, a speeding ticket, and now looking at blood flow inside my body.
It really is amazing, isn't it? It just shows how universal wave principles are. It doesn't matter if it's sound in air, sound in tissue radar waves, or light from a star relative motion causes a frequency shift.
The material also mentioned aircraft speeds at airports. I guess that's similar to police radar.
Yeah, essentially, Doppler radar systems adapted for tracking aircraft, and sometimes even weather patterns by looking at the motion of raindrops or wind.
And checking a baby's heartbeat, fetal pulse.
Right. Fetal monitors often use Doppler ultrasound, too. A probe on the mother's abdomen sends ultrasound waves towards the baby's heart. The moving heart muscle and valves reflect the waves with a Doppler shift. The monitor detects this shift and converts it into the sound of the heartbeat you hear or a heart rate number on the display. It's a safe way to check on the baby's well-being by measuring the motion of its heart.
These examples really drive home how useful this effect is. Okay, to really make sure we've got the calculations down, maybe we should walk through those work examples from the material. Pages 54, 55, the ones for the trains.
Good idea. Applying the formulas is the best way to solidify understanding. Example 1 has two trains, A and B, both with whistles blowing at 1,000 hertz. And the speed of sound in air, V, is 340 meters.
Okay, part 1. What frequency does the driver of stationary engine B hear from train A if A is moving away from B at 3 meters?
All right, let's break it down. Source is A, moving away. Observer is B, stationary. Source speed US local is 3,000. Observer speed $1. Wave speed voltagoles with 340 lead meters.
Original frequency $5 equals $1,000 hertz. Which formula applies here?
Source moving away, observer stationary, that was 5 frac plus US. Perfect.
You gotta plug in the numbers.
Okay, 5F frac 340 plus 3 times $1,000. That's 5 times $1,000.
Right.
And 343 D33 is about 0.991 something, multiplied by 1,000.
Gives about 991.3 hertz, which is what the material says. And it's lower than 1,000 hertz, which makes sense for moving away.
Exactly.
Part 2. Now, what frequency does the driver of stationary engine A hear from train B if B is moving towards A at 3 meters?
Okay, now source is B, moving towards observer is A, stationary. So 1 F 3 $3, 1 F is $5, $1,000, no loss. Source moving towards stationary observer, that was 5 F3V US out of source. Spot on. Plug them in.
4F for F times $1,000, so 5 times $1,000.
And $340 diff 337.7 is slightly more than 1. About 1.009 maybe, times 1,000.
It's 1,009 hertz. The material uses 1,009.2 hertz in its calculation, so let's stick with that. Higher than 1,000 hertz, which makes sense for moving towards.
Perfect logic.
Part 3 then asks about beat frequencies. If both drivers hear their own 1,000 hertz whistle and the whistle from the other train simultaneously.
Ah, beats. This happens when you hear two sounds with slightly different frequencies at the same time. Your ear perceives a fluctuation in loudness. The frequency of that fluctuation, the beat frequency, is just the difference between the two frequencies you're hearing.
Okay, so for driver A, they hear their own whistle at 1,000 hertz, and they hear B's whistle coming towards them at 1,009.2 hertz. The beat frequency is the difference.
Yep. Absolute difference. 1,009.2 in 1,000 hertz.
Which is 9.2 hertz. So A hears the sound get loud and soft 9.2 times a second.
Right. Now for driver B, they hear their own whistle at 1,000 hertz, and they hear A's whistle moving away at 991.3 hertz from part 1.
So the beat frequency for B is 991.3 $1,000 hertz.
Which is $8.77 hertz, or 8.7 hertz. So B hears beats at 8.7 hertz. The material says 8.8 hertz beats. For B, minor discrepancy may be in rounding or their initial calc, but the principle is the same.
Yeah, the key idea is clear. The Doppler shift creates a frequency difference, and that difference leads to beats.
Okay, ready for the trickier one. Example 2, which is part 4 in the material. Now, both trains are moving in the same direction. A moves at 1 meters, B moves faster at 3 meters. Both still emit 1,000 hertz. What frequency does driver A hear from B, and what's the beat frequency for A?
Okay, both moving. This is where we need that general formula. 5 FE of E, will, left. SUR.
Right, let's define things carefully. We want the frequency A hears from B, so B is the source, A is the observer.
Okay, source frequency $5 is 5 hertz. Wave speed $5, 343 meters. Observer A's speed is $1, almost 1 meters. Source B's speed is $1, is 300 meters. Both moving in the same direction. Let's say that's the positive direction.
Now the signs. Observer A, speed $2 equals 1, 1, is moving in the positive direction. Source B, speed $33, is also moving in the positive direction and is faster. So relative to A, B is moving away.
Right, the distance between them is increasing. Okay, let's try our sign logic. Observer A is moving away from where B emitted the sound, since B is moving faster in the same direction. Moving away means we use MCQs dollars in the numerator.
Good. Now the source, B is moving away from observer A. Source moving away means we use plus U dollars in the denominator.
So our logic suggests the formula should be 5V plus U of V plus US right. Let's quickly check the material solution.
Oh.
Okay, the material applies it as $5 plus US right, SFE SOB $2.12.
Miss. This sometimes happens depending on the exact sign convention being used, relative to medium versus relative direction of wave. To match the example's result, let's just use the specific form they applied in their solution. It likely implies a convention where speeds are positive and the signs depend purely on direction relative to the medium wave propagation in a certain way.
Okay, proceeding with the materials application, 5 left, frac V plus US right. We plug in We3 $4, 1 L 1, US 3 3, 1,000 left. So 5 L left plus 1 340 plus A right.
That's 5 L to slate times the $1,000. And 341 Ds for 343 is roughly 0.994?
Yeah, 0.994169 times 1,000 gives about 994.2 hertz. It's the value in the material. So driver A hears B's whistle at 994.2 hertz.
Okay, and the second part was the beat frequency for driver A.
Right. A hears their own whistle at 1,000 hertz and hears B's at 994.2 hertz. The beat frequency is the difference, $1,994.02 hertz.
Which is 5.8 hertz, so A hears 5.8 beats per second. This combined motion example really tests the application of the formula. Working through these calculations is great, and it naturally leads to thinking, what happens if the source speed at US of D gets really high? Like, what if it gets close to the speed of the wave itself?
Yeah. Looking at the formula for source moving towards, should it after E gets close to $1, the denominator US gets close to 0.
Right. And dividing by 0. Well, the frequency would mathematically approach infinity. That tells us the formula breaks down. Something different must happen physically.
So what does happen if the source moves exactly at the wave speed, US equals V the level?
Imagine the source spitting out wave crests. If it's moving forward at the same speed as the crests it just emitted, those crests can't get away from it in the forward direction. They all pile up right on top of each other, right at the source.
A massive pileup of wave energy.
Exactly. And what if the source moves even faster than the wave speed? Supersonic speed to the others.
Then it's actually outrunning the waves it creates.
It is. The wave fronts it emitted earlier are left behind, but they still interfere and pile up, not right at the source anymore, but along a kind of V-shape trailing behind it.
That V-shape.
Mm-hmm.
Is that the Mach cone shown in figure 6.6?
Precisely. When a source moves faster than the wave speed in the medium, it generates this conical wavefront. It's not just one crest, it's many crests arriving all at once, creating a boundary of intense pressure. This is called a shock wave.
And if I'm standing on the ground and that shock wave passes me?
That's when you hear a sonic boom. It's a sudden, very loud crack or boom sound caused by the abrupt pressure change as that cone of compressed air sweeps past your ears.
Like from a supersonic jet.
Exactly. When a jet breaks the sound barrier, it creates these shock waves that we hear as a sonic boom on the ground. The material also mentions the crack of a whip. The tip actually moves faster than sound, creating a mini sonic boom. And figure 6.7 even shows pictures of shock waves from a supersonic bullet.
Wow. So the Doppler effect describes the frequency shift up to the wave speed, and then beyond that, you get this totally different phenomenon of shock waves and sonic booms. It's all connected to that wavefront pileup.
It really is. It's quite a journey, isn't it? From just noticing the pitch change of a siren
to understanding wave compression and stretching, deriving formulas, seeing redshift from galaxies, how radar guns work, how doctors check blood flow.
And even understanding sonic booms. The Doppler effect, this consequence of relative motion, it really threads through so much of physics and technology.
It definitely goes way beyond just the sound of things moving. For anyone studying physics, getting this concept right seems essential. It's not just about the formulas, but really visualizing how that motion changes the waves we perceive.
Absolutely. Whether those waves are sound in air, ultrasound in your body, or light across the cosmos.
So what does this all mean, really? It's kind of amazing that just by measuring these tiny shifts in frequency or wavelength, we can figure out how fast things are moving, even things incredibly far away or hidden inside us.
It tells us there's so much information carried by waves, and understanding motion, specifically relative motion, is often the key to unlocking it.
It really makes you think. What other subtle effects of motion might be shaping how we perceive the world? Maybe things we don't even notice yet.
That's a great question to ponder. But for now, the next time you hear that neo-doo-woo-woom of a passing car, or maybe read about astronomers measuring galactic speeds,
You'll know it's the Doppler effect at work. The same fundamental physics, playing out on vastly different scales.